So this is a demo for running FreeRTOS on the SAMD21 Nano Curiosity board using MPLAB X. I'm currently running MPLAB X IDE version 5.40. Looking at the properties of the project, I'm running SimSys 5.4 and the DFP at 3.398, XC32 version 2.141. Now, why do I mention this? Because as things evolve, the settings actually might change. So I am running this board that you see in the left bottom corner. It has the LED glowing, and it's the SAMD21 Nano Curiosity board on an adapter board, and there are two different boards on it. There's the relay click board, and there's a Bluetooth board, which you can't see because I'm not using it right now for this demo. There's also the Explained IO Expansion Board Pro, which is this blue little attachment on the top left. Looking at the software, I've got SerialCom5 configured as UART on these two pins. It's SerialCom2 is used as receive. SerialCom pad 0 is used as TX. I've got the ADC configured for 2 volts software trigger and reading ADC in pin 1 using a reference of internal ground. Looking at the pin settings, the relay is actually connected to PB9, which is somewhere around here. This pin, I guess, relay 1. It's a GPIO, and I've got my light sensor, which is on ADC AN1. It doesn't have the ADC AN0. That's why I have selected channel 1 here. I've got some the LED, and then there's the serial communication pads. Now, why SerialCom pad 5? Because these are the ones that actually connect over this here, and they are used as the CDC channel for the debugger. So instead of using external serial communication system, I'm using the onboard CDC here. So that's the data that you see on the PuTTY terminal on COM7. Looking at the application, let me go back. The RTC has standard configuration. The RTOS cores running at three applications 0, 1, and 2. I've got, if I look at application, if I look at the main, I've done an ADC enable, and beyond that, no additional code has been added. If I look at app 0, so app.c, which is this file over here, my task basically puts a value v1 in, and I've got a queue. So inside somewhere, I've added a XQ. So there's actually, it's an app.c. So I've created a XQ, and I create this here, initialize it here, and then over in my task, I add the value 1 or I add the value 2. When I add the value 1, I add a delay of about 1 second, and that's what's making this LED glow. How I'll get to that in a second. And the other one is 500 milliseconds delay, after which this is sent back. So this is actually a loop. So this is my primary task. If I look at app 1 task, it looks at the queue. If it finds that there's a 1 there, then it toggles the LED. If not, then it just bounces over. So there's a task delay which I can technically remove, but I just add it because I know that it's going to be slower. Over in app2.c, I look at the ADC. I do an ADC conversion start at the top, then I wait for the conversion to finish because this is a software triggered conversion. I store the resultant ADC result, which is an unsigned integer over here, and then if the value is greater than 1000, then the relay is sent, otherwise the relay is cleared. I also do a peek, which is if the queue has the value 2, I actually write the value to a UART. So the way you write stuff to the UART is using SerialCom usort write. And so if I look at the main app, my first app just sends this value into the queue, and after that 1000 millisecond delay, which is basically toggling the LED. Actually, it's a total of 1500 milliseconds, which is the delay for this LED. You can configure it the way you want. I've got, and after that 1500 millisecond passes, you see that it actually writes the value of whatever it reads from the ADC onto here. Okay, let me go back one more time into the ADC configuration. ADC software triggered, ADC channel 1, internal ground, and that's about it. Inside this, if you see this value kind of updates after about 1.5 seconds, on the corresponding end, I'm doing the ADC compare conversion against a fixed value at a much higher frequency. So I've got a light sensor that I've got right there, and I'm going to block it, and it should be independent of this 1500 millisecond delay. So hear the clicking noise of the relay. Let me just move the mic. As you can see, the ADC is being read at a much faster rate, but it's just being written to the UART at a much slower rate. This task is independent of the queue itself because I've set a delay. If there's nothing in the queue, don't do anything, and I have to set the value. Note that when you use queues, I use peak because if you use receive, then it's going to delete whatever is in the queue, and then you have to put it back. So yeah, that's the demo. The code is going to be available on GitHub. This particular project was done as a demo project for a road test for the Microchip kit. Link will be in the YouTube video. And if you're watching it on Element 14, go to the YouTube video, subscribe and like, and thank you very much. Have a good day.